So part 2 of this lecture, we're picking up with question number 19. We are going from 0 to 2 pi, finding all solutions to this equation right here, 3 sine squared x minus 7x plus 2. Okay, so the way that we want to do this is using the zero factor property. Notice that we have a quadratic. So we're going to go ahead and use some sort of substitution for sine. You don't have to do this, but you may find this helpful. Okay, so pick some variable other than the variable in the problem, such as u. Let u equal sine of x. Then we have 3u squared minus 7u plus 2 is equal to 0. So now we're going to factor this quadratic. And set each equal to 0. Each factor. Okay, so once you get to this point, you can then solve for u. And replace u with what u is equal to, sine of x. Now, the sine of any angle can never exceed positive 1. So, if you're asked to solve an equation like sine x is equal to 2, well, there's no solution to that, okay? So that one you're just done with. There's an empty set, no solution to that equation. For the other equation, you have two solutions, right? 1/3 is about a third of the way up. You've got a dot over here in the first quadrant and a dot over here in the second quadrant. And we figure out this one right here using arc sine on the calculator. So we'll go ahead and do that. Arc sine of 1/3 is about 0.3398. And then to get your other value right over here, this is going to be pi minus 0.3398. So you go back to the calculator again, and we have pi minus 0.3398, and that would be 2.8018. And now go back to my open math, and my values are 0.3398 and 2.8018. It didn't tell me where to round. You're not going to get in trouble if you stop at the 4th decimal point, okay? So when in doubt, just go out 4 decimal points. That's the furthest out I've ever been told to round. For these problems is the 4th decimal. So that would be a good place to stop if you're not instructed to stop in a particular place. Okay, now question 20 is basically the same concept, except that you're going to be solving this in terms of 0 to 360. So do the exact same problem. Substitute sine beta. Use u is equal to sine beta. Factor it out. Do it the exact same way we did question number 19, except your answers need to be between 0 and 360. So that means that when you use the calculator, make sure you switch from radians to degrees. Okay, now this one has a video, and it's going to be the same type of problem. It's a factoring problem, except that you're doing all solutions. So you would want to be adding on 2 pi k, right there, 2 pi k. Okay, so now question number 22 See, I'm really nice. I tell you to use the quadratic formula. Really, use your textbook as much as possible. Go through these problems with the textbook, and it's going to be really helpful. So I'll go ahead and work with you on question number 22 now. Okay, question 22. So first of all, this does not factor, okay, even if you want to use the U substitution, which I still recommend. Anytime you have a quadratic, you go ahead and use the U substitution. You can rewrite this now as 2u squared plus 2u minus 1 is equal to 0, and you try to use, you try to factor it, and it won't factor. So now we want to use the quadratic formula. Instead of x equals, we have u equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that would be negative 2 plus or minus the square root of, let's see, 4 plus 8 would be 12. Now we want to simplify the radical. Okay, and then we factor out a 2 from the numerator. And we write this, our final answer here for u is equal to negative 1 plus or minus root 3 over 2. Okay, so then, of course, u is really cosine of theta. So cosine of theta is equal to that value. All right, so then what you're going to want to do is you're going to want to ask the original problem, radians or degrees? Radians, and 0 to 2 pi radians. Okay, good to know. So we would want to draw a circle. We're going to have two different values that we're looking at here, so possibly 4 solutions. So one of the values is negative 1 plus root 3 over 2, which is some sort of positive value. Okay, so the first notch on the x-axis would be negative 1 plus root 3 over 2 is a positive number, and it's going to yield 2 dots, right? The other one is a negative number, which is negative 1 minus root 3 over 2, and then that would also have 2 dots on the unit circle. So we have a positive notch on the x-axis for the positive version of this number, and then a negative notch on the x-axis for the negative version of the number. And now we want to figure out what these points are right here using the inverse cosine. So now we go back over to the graphing calculator. We are in radians, so we want to use inverse cosine of, let's see, my numerator is negative 1 plus the square root of 3. And then I'm going to divide that number by 2. And I have a value here of 1.1961. If I round out to 4 decimal places, I might go ahead and write 0.6 so that I don't make a rounding error. Okay, so that's one of my values, and then my other value is if I change this positive to a negative. Cosine inverse, undefined. Ooh, why is that undefined? Well, negative 1 minus root 3 exceeds negative 2. And if the numerator exceeds -2 and we divide by 2, then this number right here is exceeding -1. So really, this notch, if this right here on the unit circle is -1, 0, this notch is not even on this side of the axis. If you extend this x-axis back, the number really is way out here. So there are no other two dots. This is -1 minus √3 over 2 is actually less than -1. So on the unit circle, we cannot go past -1, and this number is less than -1. So I didn't think about that at first. I was just paying attention to positive or negative, so it's a good thing the calculator caught that for me. Now, for this other dot right here, we get this by taking 2 pi and subtracting from 2 pi the value of the angle, because we know that we have two congruent angles, right? So this angle right here is congruent to this angle right here. Okay, so let's go back to the graphing calculator now, or the scientific calculator rather, and we're going to take 2 pi and subtract from 2 pi 1.19606, and we get 5.0871. So now when I go back to my open math, and I type this in, oh, this one only rounded to 2 decimal places. And this is actually 1.20, so I really didn't need to go out so far. But yeah, this number right here rounded to 2 decimal places is just 1.20, and then this one would be 5.09, just like we see here on my open math. Okay, so to do a problem like this, we're going to be using a Pythagorean identity to simplify the equation. And there's a nice video right here that will walk you through how to do that. But the basic idea is that you're going to replace, in this case they have sine theta plus 1 is equal to 2 cosine squared theta. In your actual problem here, it's cosine theta plus 1 is equal to 2 sine squared theta. So I imagine you're going to, or alpha, these are alphas. Alpha, this is alpha. So the idea is that sine squared plus cosine squared is equal to 1. So you can replace your cosine squared with 1 minus sine squared. Just like you could replace over here your sine squared with 1 minus cosine squared. And that way you'll get something entirely in the form of one trig function. So let me do this one quickly on the board for you. Okay, so first what I want to do is I want to replace sine squared alpha with 1 minus cosine squared alpha. And now I only have one trig function, you see? Get everything on one side. And now from here, you can just factor. Factors of 2 that differ by 1 are 1 and 2. So yeah, this one will factor. But the trick is, how do I get to something that does factor when I have 2 trig functions and a constant? So what you would do is you would use one of the identities to figure out a way to rewrite your equation so that you only are using one trig function. And now we come down to the last 3 problems. For these problems, we're supposed to be using the square root property. So let's start with the first one. If we were to rewrite this equation where we get sine squared all by itself, what would we have? We would, of course, have sine squared x is equal to 3 over 4. Now what we would want to do in this case is use the square root property. Now when you use the square root property, always remember, first of all, your radical needs to go down over the entire fraction, not just the denominator. And secondly, at least one of the sides, just one of the sides, picks up this plus or minus. So then what that does is that when we simplify this further, the left-hand side, of course, becomes sine of x, and the right-hand side becomes plus or minus the square root of 3 over 2. So sine x is equal to plus or minus square root of 3 over 2. So next what we do is we look at the unit circle, and we find the 4 values where sine is equal to either positive root 3 over 2 or negative root 3 over 2. And those values are at pi thirds, 2 pi thirds, 4 pi thirds, and 5 pi thirds. So it will be the same type of problem for question number 29. I will do question number 29 on the board. So the first thing we want to do is we want to get secant squared by itself. Divided by 5 will be 4. And then we want to take the square root of both sides. When you take the square root of both sides, remember that you get a plus or minus when you use the square root property. Okay, so if you have a secant theta equal to plus or minus 2, that means that your cosine of theta is equal to plus or minus 1/2. And we are doing this in degrees, so we look for all of the values of cosine in degrees where your cosine value is either positive 1/2 or negative 1/2, and we get that from the unit circle. So your values are 60, 120, 240, and 300. Now, of course, you could end up with values that are not on the unit circle, and that's what you'd end up with in this case. Actually, no. Yes? Square root of... you do. That's still in the unit circle. Yep, those are still unit circle values. So it will be the same type of problem. So, really, question 30 may have been redundant after question number 28. So once you get question number 28, question 30 should be a breeze, and you should feel very good about this concept. Well, that's it for 6.2. I hope you enjoyed these trig equations. They should be a nice fresh breeze after your proofs that you did in the previous chapter. Chapter 5 is a hard chapter. But as you continue to work through these problems, just try to stay on top of old content as much as possible as you prepare for the test. And anything you can do to work ahead will also be really helpful for you because it will give you more time to review for the test.